Hi there and welcome to our latest edition of our Flip Learning class. Now in today's lesson we're going to be looking at metallic bonding and the structure of the periodic table. So it's a bit of two things kind of mashed in together. Anyway, I hope you enjoy this. Here's our objectives. Okay, so we are looking today at metals and the periodic table. So by the end of this video you should understand our objectives for today, which are to look at the properties of metals and to look at how the periodic developed over a period of time. Okay, now we're going to look at what metals are. Now metals make up most of the periodic table, but they have an arrangement where they look like this. So you can see that all the particles are arranged in a fairly uniform way. Now they're held fairly close together and fairly tightly packed because they're fairly strong attractions to each other. Now each of these metals is a positive ion, which means they have a positive charge. Now the reason they have a positive charge is because they have lost ownership of an electron. Now these electrons are close by and they are around. Now these electrons are held by the positive ion, because we need to remember that these electrons are negatively charged. So these electrons are held, which means they don't belong to any of the particular ions. Now this is called a delocalized system. So delocalized So these electrons are delocalized, which means they have the ability to move. So for example, this one can move around this positive ion, and this one can move as well. This is why all metals are able to conduct electricity and heat, because electrons will move. So this one will come close to this one, causing this one to repel and move on, causing this one to repel and move on. So we get this movement of electrons, which is electricity. And here we have a slightly better drawn. So we can see the positive ions with the negative electrons that are able to move backwards and forwards. Superconductors are able to conduct electricity without any resistance. Now if we look at our metal ions with our electrons, now as we get these electrons moving through the metal, there is heat generated. Now the heat is caused by this force of attraction between the positive and the negative ions. Now with a superconductor there's no resistance, there's no attraction between the electrons and the positive ion, which means that they can get a much better conduction rate. Now for conduction to happen, or why we need conduction to happen without any resistance, is for medical scanners, electrical circuits and powerful magnets. Now you can see here this is one of the superconductors in a particle collider, such as the Large Hadron Collider at CERN, and you can see that we've got the superconducting metal here and here, which will allow the electromagnet to be able to direct the particles in the way that they want. Now ideally they want to be able to develop superconductors so it can run at room temperature. At the moment, with the one at CERN, it has to run at about minus 271 degrees, and I think the highest temperature we're at the moment is about 200 degrees. So we're looking at trying to develop that technology so that we can get superconductors at room temperature. Okay, now we're going to move away slightly from metals, and we're going to look at the periodic table and the whole structure of the periodic table. Now, we've got the periodic table here, and we're going to look at how they're actually ordered. Now, if we start with group, or the first element here, hydrogen, and we go across to helium, and then lithium, we tend to go across from left to right, and then down. So we go in ascending order this way, and this order is based on the atomic number, which is just here. So we start with 1, go to 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, all the way through, with the lanthanides and actinides fitting in just in this section here. They're normally put underneath for ease of drawing. Now, the first scientist to try and put them into an order was this man here, Johann Dobrynia. And what he did is he arranged the elements into triads. Now, triad means 3, and how he did this is to arrange them in order according to their properties. So chlorine, bromine and iodine all had similar properties. What he also found out was that the mass of the second one, so the middle one, was an average of the other two, so the lighter one and the heavier one. And this meant that he could put the whole order, or change the order in which they went in. And this was actually completed by another scientist called John Newlands, and he arranged the atoms in the periodic table according to their atomic weight, and he noticed that every 8th element had similar properties and coincided with the triads previously identified. Now, this became known as the law of octaves. But it wasn't until the Russian scientist Dmitry Mendeleev came up with a better way of doing it, and he looked at the properties and the reactions that the different elements had, and there was often conflicts with how John Newlands had arranged them, because there were a couple of elements that didn't quite fit the pattern. Now, if we look here, okay, we can see that iodine and beryllium, okay, iodine is lighter than beryllium. Now, Newland had beryllium here and iodine here. Now, all Mendeleev did was swap them around, because beryllium has similar properties to these elements and iodine has similar properties to these elements. And that's how we've come up with this periodic table that we have today, and this is Mendeleev's idea. Now, Mendeleev was very clever, because he actually had gaps in the periodic table, so there were elements that hadn't been discovered that he left spaces for, so that they could be put in once they'd been discovered. Okay, now in previous lessons we have mentioned groups and periods before, but we'll just go through this again and just clarify what we understand for this. Now, a group is one of the vertical lines going down. So these are all groups. Now, as we've seen, or will see, with the alkali metals and the halogens here, alkali metals here, they all have similar properties and have similar reactions. Now the other thing that links the groups together is their electrons in their outer shell. So here, lithium through to francium, they all have one electron in the outer shell, which is often why you see hydrogen in that group as well, because they have the one electron. And then we have the 2 electrons, 3, 4, 5, 6, 7, and then a full shell at the end. Now that's a group. A period is where we go across. Now periods have different numbers of electrons in that outer shell, but they do have the same number of shells. So this first period has 1 shell, 2 shell, 3 shells, 4 shells, and so on. Okay then, so let's just recap what we've been looking at then today. We have looked at metallic bonding and the structure of metals and how we can get metals to conduct electricity and heat by that movement of electrons through the particles or through the positive ions. We've also looked at superconductors and how they are able to provide electricity without any resistance. And we've also looked at the 3 scientists that have developed the periodic table and how we now know some of the rules that we can apply when putting chemicals into that periodic table. Anyway, I hope you've enjoyed it, and I will see you next time. Bye.